this video, I want to walk through an example problem which involves damped free vibration and see how we can make use of our understanding of those equations in order to evaluate the problem. So the setup of the problem is that we have a 30,000 pound mass rolling on some frictionless wheels, and it's moving with some initial velocity until it makes contact with this plate here, which is intended to stop it. And the plate is attached to a spring and a dash pot in order to provide damped oscillation. So the setup of the problem is that we don't know the spring constant and we don't know the damping coefficient of the dash pot, but we observe the motion of the cart, of the mass, when it hits the stopping plate. And if we plot it, we see that it has a sinusoidal output, so we know that we have an underdamped system. Recall that only underdamped systems exhibit that sinusoidal output. And we see that there is a 0.4 second gap or period of that oscillation. And then we observe that the first peak of the oscillation is 1/2 inch and the second peak is 1/10 of an inch. So from that data, we want to figure out what sort of setup we have here for our mass spring damper system. So the first thing that I'm going to do is convert the weight of our cart to mass. And we get 931.68 pounds second squared per foot. Now, ultimately, recall that the equation, the standard form equation for this looks something like this. M double dot plus Cx dot plus Kx equals 0. So this is that standard form equation for damped free vibration. And also recall that we have an equation which is for an underdamped scenario, which looks like this as a solution for the position x. And the key thing that we need to keep in mind is that this parenthetical part of the equation defines the sinusoidal pattern that we see in the output, and this first term here defines the damping of that sinusoidal output, so the reason that the peaks get smaller over time. So that's kind of useful as we get through and start thinking about what's actually happening. So before I make use of that, though, I want to take note of the damped period, which is given as 0.4 seconds, and that allows us to calculate the damped natural frequency as 2 pi over tau d. And we get 15.708 radians per second. So now the key is to kind of figure out how we can make use of this information in order to actually evaluate the problem. So I mentioned that this first term defines the decrease in our plot. And recall in my previous video that I said we have an envelope that kind of shows that decrease, which is defined by that first portion of the equation. And therefore, I should be able to calculate these x positions, because they're at the peaks and they're contained within that envelope. I should be able to calculate those. Looking back on my equation, I have a time, oops, just realized I labeled this tau, meant to label it with a time t. So I have a time t showing up here, and I know something about that. I know what's happening between these 2 points. I know my mass, but I don't know my coefficient. So what I really need is some relationship then between my peak value x and my time t. Now I don't necessarily know from this plot where this first peak occurs, but if I think about what I have happening, I have 2 different times, and we'll call this right here time t, and we'll call this position, the second peak, t plus tau d, since I know what tau d is. Now, that means that I can take the relationship between those two and do something with that. So what I'm going to do is I'm going to say, let's take the second position over the first position, and then set that equal to e to the minus c over 2m. And my time again at my second position is t plus t tau d. Now for the first position, e to the c over 2m, and my time corresponding to that position is just t. So you can probably see where I'm going with this. When I divide 2 things and I have exponents, I subtract those exponents, or I can subtract those exponents in order to represent them as a single exponent. So if I do that, what I'm going to see is everything is the same except for this t plus tau d and this t here. So if I subtract t minus t, those are going to drop out, and I'm left with then e to the minus c over 2m tau d. So if I can specify the ratio between these 2 peaks, I can use this to solve for my coefficient over here, c, because everything else in this is known. So I'm going to go ahead and rewrite this then in order to solve for that coefficient. So first I have to get my coefficient out of the exponent. Well, because this is base e, I can take the natural log of that in order to undo it. So I get c over 2m tau d, and my negative sign, I can take care of that because the negative sign in the natural log just flips the ratio. So I can say that that's equal to ln of x1 over x2. Now I can multiply my 2m across, divide my tau d, and solve for c. So a little bit of math stuff in there, but once we've got that rearranging taken care of, we have an equation that we can go ahead and solve for c. So I'm going to plug in my numbers now. My mass was 931.68. My period of oscillation was 0.4. And my ratio is 0.5 or 0.1. So this gives me a coefficient c of 7,497.3 pound-second per foot. So that's the first thing that I was trying to solve for. The next thing I'm looking for is my spring coefficient K, or my spring stiffness. So the thing that we haven't used here yet is our damped natural frequency, omega d. So if I look back at the equations that we had available to us, One of them was in terms of what the solution for the damp natural frequency is, and we saw that it was k over m minus c over 2m. And because I just calculated c, the only unknown in this equation now is k, and I can go ahead and make use of that. So I've identified an equation that has the unknown that I'm looking for, k, and has other things that are all known to me at this point. So I'm going to go ahead and rearrange to solve for k. And I can plug in my values. And solving this, then I get that k is equal to 244,963.5 pounds per foot. So it's a relatively stiff spring causing this oscillation. So to summarize, basically what I've done is I've taken kind of a different approach here to many problems, in that I have the output, I have the result in the oscillation and what the response of the system is, and I'm using it to back calculate my properties and try to figure out what my coefficient for my dash pot is and what my stiffness of my spring is. All right, thanks.